everybody, let's give this problem a try. So we have a frame. So why don't we try starting off solving for the reactions at these supports. So A, B, I'll call this C over here. Okay, so here's the free body diagram of the entire structure. Then I'll decompose the reactions at pin A and pin C over here. And then there's a distributed load, which I'll represent as a single discrete force. Let's see, so that's 3 times 400 is 1200. Located at the centroid, it's just a rectangle, so just in the middle, 1.5 meters. Okay, so let's solve for these reactions. Okay, so in the x direction we have AX, CX. In the y direction, AY, CY, minus 1200. Let's see, I want to solve for what's happening in beam AB. So I'm going to sum torque about over here. Okay, so let's see, this is 2 meters. So that's minus 2 meters times AX. Here to here is 1.5 minus 1.5 meters times 1200. Okay, so AX is 1800 over 2 is 900, minus 900. And then CX is just opposite of that. And we don't have enough information to solve for AY and CY. That's statically indeterminate. Okay, but that helps a little bit. So what do we do next? Break it apart. So let's break it apart. Okay, so this member only has forces acting at these 2 points. So it's a 2-force member. So I'm just gonna go like this. So then these have got to be equal and opposite. I'll just call it some unknown tension 1. Okay, and then this one member over here, has forces acting at these 2 points. So also 2-force member. So like this. So these have got to be equal and opposite, which means these 2 have to be equal and opposite. I drew them in tension, so I'll just call it tension 2 for a lack of creativity. Okay. And what else do we have going on? There's the reaction at C. Okay, so we already got that. That's 900, so that helps a little bit. CY is still unknown. AX is minus 900, so this way. That helps a little bit. AY is still unknown. Okay, and then we have the distributed load acting over here, which I'll just, again, draw as a discrete force acting at the centroid of the shape. Okay, so then let's just take this one and this free body diagram. Okay, so in the x direction we have, okay, so we need this angle over here. Let me draw this a little bit bigger so you can see. Let me draw that angle right here. Okay, so that angle is actually this angle right here. And if we look at this triangle, tangent is opposite over adjacent. Okay, so theta equals arctangent of 2. So just punch that in the calculator. Now we know the angle. So back to this free body diagram. In the x direction, we have minus 900 minus T1 cosine theta. And that's it. Okay, y direction, we have AY minus 1200 minus T1 sine theta minus T2. Okay, and then let's sum torque about wherever we feel like. How about over here? Okay, so there's, okay, here to here is 1.5, so minus 1.5 times 1200 newtons. And then here to here is 2 meters, right? So minus 2 meters times only this component, so t1 sine theta, and then here to here is 3 meters, minus 3 meters times t2. Okay, what do we have here? Let me point out the unknowns over here. Okay, so we should start here. So t1 is minus 900 over cosine theta. t1 is minus 900 over cosine theta. Let me just punch that in the calculator. Okay, so that's 2012. Okay, and then we can take that and plug it in here and solve for t2. So so that's this divided by 3. Let me punch that in the calculator. Okay, so that's 600. And then we know t1 and t2, so see right here, we can plug that in and solve for ay. So ay is 0. That's interesting. Okay. All right, so we have everything we need for this bar already. Okay, so we could stop here and then, you just draw, for this free body diagram, you can write as many as 3 more equations and then solve for this unknown. But we don't need that for this particular question. Okay, so here's the bar. Let me just fill in the numbers. Okay, so this was 900. AY was 0. Okay, T1 was minus 2012. Let me just decompose this so it's actually this way, 2012. And then if I just punch that cosine, then this way would be 900. If I'm decomposing this vector, and then this component would be 1800. Okay, so again, these two are the components of this. I just split it into components. And then T2 was 600, so that's this way. And there's the distributed load over here. Okay, let me check to make sure I wrote everything down. Okay, we've got the reaction, the reaction, the reaction. Okay, we're good. So now, and let me make note, what is this loading curve? It's a constant. The loading curve is a constant 400. Okay, now let's practice using the calculus version of shear force and bending moment. Okay, so dv dx equals minus w, the loading curve, which in this example is 400. Okay, so let's say we want to go from here to here, right? Because on this side of the bar, there's definitely nothing happening. There's no shear. So just 0. And then over here, we start to experience this distributed load up until here, then something else happens, right? We have this. So from 0 to 2, so this is between 0 and 2, this. Right, let's move dx on this side, and then integrate both sides. From 0 to some other x between 0 and 2. Okay, so then we have v minus v at 0, which is in this case 0, minus 400x. Okay, so between 0 and 2, it looks like minus 400x. So the slope is minus 400, like this, which means at x equal to 2, this has got to reach minus 800 down over here. Minus 800 right here. Okay, but then suddenly we encounter this, right? So then it goes up 1800. It goes up 1800, which means it's got to reach 1,000, positive 1,000 newtons. Okay, and then what happens over here? Again, we experience that distributed load. Let me do this again. So now we're between 2 and 3. So between 2 and 3, dV dx equals minus W, which in this case is 400. So move dx over here and then integrate both sides. But now we're integrating from x equal to 2 to some other x between 2 and 3. So this is v at x equal to 2 to some other v between 2 and 3. So v minus v at 2 equals minus 400 x minus 2 like this. Okay, right? And what is v at 2? 1,000. Okay, so that means v is 1,000 minus 400. We can simplify this, but I'll just leave it like that for now. So between 2 and 3, what is the value at x equal to 2? That becomes 0, so it's 1,000 right over here. And then as x increases to 3, it'll have a slope of negative 400. Right, so the slope here is the same as the slope over here. And then at x equal to 3, this is going to be 4, so this is going to be 600. Right? So right here is 600. 600. Right here is 600. Okay, and then we experience this, right? So, which is in the negative direction. So it goes from 600 down 600. So to 0. So here, so this is the shear as a function of x. Okay. Now how about the bending moment? Okay, I shouldn't have erased what I had here. Okay, so this is v of x. Maybe I should simplify this now. Okay, so v of x is, so this is minus, so plus, so 1800 minus 400x. This is between 2 and 3. And then between 0 and 2, it was minus 400x, right, this. Okay, now how about bending moment? So what's the relationship? Let's take a look. There's no couples or anything acting anywhere. So the bending moment, it's 0 over here, but then nothing, there's no couple to make it change instantaneously. We just have this shear over here between 0 and 2, like this. And then what does that look like? dm dx equals v. And between 0 and 2, let me just write that down over here. Between 0 and 2, it's minus 400x. So I'll just plug that in over here. Minus 400x. Then let's move dx right here. And then integrate both sides from x equals 0 to some x between 0 and 2. So m at x equal to 0 to some other m at x. Okay, so what do we have here? minus 400x squared over 2 from 0 to x, which means this is like this, and this is 0, right? Okay, so here we go. I'll just write it right over here. Okay, and then what does that look like? It's a parabola, but then at x equal to 0, it's 0, and then as x increases, it's decreasing. So it's this half of the parabola, not this one. So it looks something like, let's say like this. All right, some parabola like that. Okay, and then at x equal to 2, that would be minus 800. Okay, so minus 800. Newton meters. Okay, now what about between 2 and 3? Between 2 and 3, same, dm by dx equals v. V is 1800 minus 400x. And this is between 2 and 3 again, right? Okay, so then let's move dx right here. And then integrate both sides from x equal 2 to some other x between 2 and 3. So this is m at x equal to 2 to some other m. Okay, so what do we have here? M of x minus m at x equal to 2, which we just said was negative 800, right? So this is negative 800. And then let's integrate this. 1800x minus 400x squared over 2 from 2 to x. Okay, so let me maybe not skip too many steps here. Let me leave this right here. Okay, so then this is 1800x minus 200x squared minus 1800 times 2, 3600. Maybe I can just write it like this. It's easier. X minus 2. Okay, minus 200 x minus 2 squared. Okay, I mean, you can simplify it, but I'll just leave it like that for now. Okay, so what does that look like? Let me just move this over a little bit. Okay, so from when x is 2, all of this is 0, so it's at minus 800. And then at x equal to 3, what do we have here? So that would be 1800, and then this would be 3, it's 200. Okay, let's see. Oops, I just noticed I wrote this wrong. X squared minus 2 squared. Okay. So at x equal, let me try again. At x equal to 2, yeah, so that's still 0. X equal to 3, right? So then this will be 9 minus 4, so it's 5,000, so 1,000. Okay, so at x equal to 3, this whole thing is 0. And then it's increasing, so it's a parabola that's increasing up to 0. Okay, and then this is between 2 and 3. So this goes right here. Right, so this is shear force and bending moment between 0 and 2. This is shear force and bending moment between 2 and 3. Okay. So keep on practicing. It takes some practice. It's simple because it's just the two formulas, right? dv dx equals minus w, and then dm dx equals v. Right, that's it. Those are the only two formulas we used. But just keep on practicing, especially when it comes to those limits of integration. Right, just be careful about those. Okay, so let me know if you have questions. See you in the next video.